Right, so nice to see most of you made it in through the lovely weather that we're having. So far in my part of this course we've been talking about Hadoop and the slightly tedious use of Java and implementing map and reduce and setup and so on to run arbitrary code on large data files of various types. And now that we've got some grasp on the mechanics of all of that and how the data moves around and the job of the map and the reduce and so on, I'm going to show you a few ways of doing the same kind of thing, but without having to worry quite so much about implementing mappers and reducers and so on. So you might think, well, why did you bother telling us about all that stuff in the first place? But you kind of need to know what's going on behind the scenes before, I tell you some easier interfaces to it. Also, it would make a very short lecture course if I just told you about these bits. So what I'm going to tell you about in this lecture is something called Hive. It's one of the growing suite of programs that Apache have produced that sits on top of Hadoop and HDFS and adds some extra functionality and, in this case, an extra level of abstraction away from writing MapReduce code. Although what happens underneath is actually the same thing. It actually produces MapReduce jobs, but without you having to do the same level of programming. So I suppose I should tell you what it is. So this is what Hive advertises itself as: a data warehouse facility for storing data in HDFS. And you'll see why they call it a data warehouse rather than a database as we go along. But there are some obvious examples, obvious reasons for that we'll see pretty soon. The first one isn't that it has an SQL-like language. It's called HiveQL. And this is the main point of it, that once you've got your data set up in Hive, you can interact with it using SQL statements. So it's a way of, behind the scenes, converting SQL statements into MapReduce jobs. Hive does that for you, and then it runs those MapReduce jobs. But the way you specify what you want them to do is via an SQL statement, right? So that makes the whole thing an awful lot more simple for you, as long as the thing that you want to do can be written as an SQL statement. And sometimes that's quite straightforward. Sometimes, for example, the assignment that you've got, maybe that isn't quite so straightforward because you can't write SQL as easily to go in and tokenize each, if they're just text sentences. It's not really suitable. So this is only really a solution in certain circumstances, those being the data that you've got is tabular in its form, right? You can impose a schema on it such that there are tables with named columns and each row is an entity. You're not really using it as a database, so while it can do things like perform joins, and so you have some kind of idea of relational integrity, it's not a database. And we'll see a number of reasons why it's not a database as we go along. It uses some of the language from databases, and it uses SQL, which really makes it feel like a database, but it isn't. It still stores all of the data in HDFS in files, and actually what it does is this next point here. It allows you to impose a schema or define a schema over those files. So if you have some files and they're set up in a tabular form, I don't know, comma separated, for example, you can say, this is the name of each column that you would expect to find in these files. This is what each file's table name is, and so on. And based on that, it allows you to query them by writing some SQL. And as I said, it then converts those queries into a MapReduce job and runs it. And that gives you this extra advantage because it ends up as Java code that runs a MapReduce. As a programmer, you can also insert some code into that process. So you're kind of augmenting. You've got your basic using of SQL, but you can augment that by adding Java code to tell it to do other things if you want to. All right, so that all sounds quite good. But there are some limitations, and here are the first insights that you might get into why I say it's not a database. Okay, we're used to the idea of a database, particularly something transactional, as having a very fine-grained access to the data. All right, like the one that your bank has for you. You can look at your details. If you move house, they change the address on your line. If your bank balance changes, they change the bank balance if that's stored in a field, and so on. All right, so a traditional database is a very interactive thing, and the data is treated at a very fine level. Sometimes you might process the whole database to do a big aggregation, but a lot of the time you're interacting. With Hive, that's not the case. All right, Hive still falls under that Hadoop HDFS use case that I talked about at the very start of this part of the course, where I said it's about streaming data. It's about appending data to the end of a generally very large and rapidly growing store of data. So remember I talked about, for example, the Formula One car going around the racing track, and it's spewing out data at high speed, and we just need somewhere to put it. All right. So we don't want the overhead of a database system of having to update tables and maintain integrity and so on every time, every hundredth of a second when a reading from the car comes in. We just need somewhere to put it. And then generally at the end of the race, we want to process all of it. Right? And we're not going back in and saying, oh yeah, you see the oil pressure at 35 minutes and 3 seconds in, we should change that to a different value. Once you've read it, once you've read it from the racing car, once you've written it to the database, that's it. So we've got this write once, read many pattern, exactly the same as I talked about before, where the idea is that you have collected this data and it's forever growing, and you're often, more than once at least, asking questions of it in an aggregation, tell me the average of this by that and so on. But the updates are basically just writing to it. So the queries tend to involve table scans. As I said, you're processing all of the data. You're not going in and saying, tell me what happened at this particular instance. So we don't read single rows. We definitely don't write single rows. You can imagine how you might read a single row, but it's still a table scan, right? So basically to read a single row, you'd have to read every row, but ignore all of them that didn't match the row that you were interested in, which is obviously a little bit slow. So it's kind of log files, web files, database files, maybe trader data, machine data, like my racing car and so on. Something that's streaming generally, and probably at reasonably high volume. So times when you wouldn't use it, well, if you can get your data into a single non-distributed database, then there's probably not much point for putting it on Hadoop in the first place, right? So if your data all fits on one machine, you have many other options for how to store it and process it. So it's going to be big before you consider Hive. If you want to access and update individual records, Hive isn't for you. Probably one of the NoSQL databases that we talked about last semester would be more useful for that. And you've probably already discovered that talking to HDFS is not a rapid activity, right? You tell it to do something, and it has to start up a JVM, and it has to run the code, and even getting a directory listing is kind of slow. So there's this high latency, sometimes minutes, to do a single query. So it's no good. You wouldn't want this running behind your website so that when somebody logs in, it looks up their username and password, and if it finds it, lets them log in. So it has to be something where latency, at least of reads, doesn't matter. You'll see that there is a very fast way of getting data into it. We don't have to do that whole start up the JVM every time we want to write in a single row, or that whole high-speed streaming of data thing wouldn't work anymore. But certainly we don't want to be asking it for single rows, generally speaking, because of the latency. All right. Even though you can consider it might kind of be possible. So, all right, so how does it go about it? Well, I've already mentioned the data is stored as normal in files in HDFS. And basically what we're doing is imposing on top of that data some kind of schema. So it doesn't have its own different database storage structure. It's just using the files and imposing a schema on top of them. So basically, aside from the files, we're saying this particular file, you will find if you look in it, has this many columns, and I want to call them, I don't know, username, first name, surname, first line of address, or whatever you want to call them. And your file has to match that. All right. So, as I said, when we access the data, we're doing a table scan, right? We're reading every single row, so some kind of aggregation generally. So it's not set up fast access to a particular row, so it doesn't have keys. There's no setting of an index, and there's no use of keys like there is in a traditional relational database. It's really just putting some of the SQL-like syntax on top of just a file, a tabular file. So we can't speed up. No keys, but there is index. We can index to speed up row selection, but you tend to be processing all of it rather than doing that. And
for each select or project, it will read the entire table rather than having specific read write.
Well, writing is always just appending. All right, you can't update. There simply isn't an update. For reading, you can index columns so that you can speed up single row if you want to, but it's not the usual use case for it. Generally speaking, it kind of table scans. And the same as the other Hadoop HDFS facilities that we talked about, it's got data compression built in. So you can put your data into an HDFS file, compress it using one of HDFS's compression algorithms, and store it compressed. And then when you run a query in Hive, it, on the fly, reads the header, uncompresses it, does the aggregation, and, well, obviously leaves it compressed in that state. Right, okay, so those are the kind of basic ideas of it. Then, as I said, we interact with it in an SQL-like way. You'll see that there are some SQL queries that you write which are exactly the same as those that you recognise, and some which are not available at all, like update, because we can't update single rows. So, for example, you can use a where clause to filter certain rows. So that's kind of equivalent in your mapper of saying if this column equals some predefined value, then do whatever you're going to do and emit it. But if it doesn't, then don't emit it. All right, so that's how that. Same kind of idea. The mapper does the filtering that's defined by the where clause. You can select certain columns from the select. So select name, comma, surname or something. And it finds from the schema which columns those are, and those are the only two that are taken out. So again, in the map method, it reads in the row, splits it into columns, and just extracts the ones that you've asked for. So that's your select columns where some column value equals something. So that's just like a normal SQL select. You can do equijoins between two tables where the value in one column in the one table matches the value in the column of the other table, just like in a normal SQL. And as you might expect, given that the type of query you're most likely to want to ask of this type of database, it's got all of the aggregations that you'd expect from SQL using the group by. So sum and average and so on, all of those. So the first difference in that list is that, oh yeah.
But he's going to do all these in the old files or in the block, in each block?
It does it as if all of the data were one giant table, even though that table is spread across. So just like MapReduce, which is what's happening behind the scenes. So you've got physically several files in several blocks and so on, but it's operating logically on the table that those come together to make. So the split is probably lengthways, right? So this block has a certain number of rows and this block has a certain number of rows and so on.
For a mean is the entire mean?
Yes, the entire mean.
Okay.
Yes. And then, of course, the group by is how you might split it up. But yeah, there's no sense in which you can ask for the mean from the block that is on a certain node. You can't even specify that. Yeah.
And what is this equijoin? Is it different from equijoin?
Now, equijoin is the same as in a database. That's where you do a join across two tables where the name of the column is the same. So if I've used user ID in this one and user ID in that one, and I tell it to do an equijoin, it spots the fact that these two columns have the same name, and those are the columns that it joins on. Same as in the database, you'll find that you can do that. Otherwise, you have to specify the column names where, this table A dot column equals that table dot B dot other column name.
It's not HLSM, is it?
Well, they're different types of definitions. So an equijoin is about the names of the columns, and the natural join is about how the columns line up. So it could, yes, it could. And that's the type of join that it does. Yeah. Okay, so, yes, go on.
It's just like this question actually arises from those two, because if all the data is treated as one table,
yeah.
how does it come that we join them? Because if we was a schema, just like virtually, and say
Yeah.
all the data in my Hadoop DHH.
No, okay, right. So it's not all of the data. When you define the schema, which we'll have a look at later, you pick a particular file and you say this file is, I don't know, users, for example. So let's say I've got a file called users.txt. It's a bad example, you wouldn't probably use it for a set of users, but I've started now. And users.txt, I don't know, maybe users are coming in so fast that you need to. And then another one, which is perhaps transactions.txt, and actually that is growing super fast maybe, and you want to know which transactions go with which users. So that's when you're doing the join across those two. Yes, your HDFS can still have lots of different files in it, and each file can correspond to a table. So that's how those come in. And then yes, finally, when the same again as MapReduce, you'll know that you run the MapReduce job and it spits the results out into a file that it stores on HDFS, right? And so similar concept here. You run the query, and the query is dumped. The query results are dumped into a new file in HDFS, but which is already set up as a table. Okay. So if you've said select A, B, C from D, the table D, then you'll get a new table, whatever you called the query, with A and B and C in it from those, from that query. Does that make sense? So it's just, that's where it gets written to. You're probably used to the idea that you do a query and, I don't know, it appears in the command line or it's available to some program code to do something with. But because we're not doing transactions, because we're running a big job and then looking at the results afterwards, it's written to another table. So instead of that directory /r part 00000, it's written into a table already for you. Which then you have to read, of course. So is that what you were going to ask? How do we see the contents of that table?
Yeah, it's like in Hadoop where you basically you have to move between each job these output folder away from the.
Oh, so it doesn't overwrite it?
Yeah, it doesn't overwrite, it fails.
Yes, it won't overwrite it.
Yeah,
yes, just give it a different table name, or remove that table. They're just files again.
So basically it doesn't do, doesn't append just.
That's it. Yes, and because it's just a file, when you want to see the final results, you, same as in, you catalogue the contents of that. Or you'll see, I'll show you in a few slides' time, that actually you can tell it to write that table to your local store instead of onto HDFS. So it's then just available for you to do what you want with. So yes, it stores it in HDFS. You can manage the tables and these things, the partitions, which I'll come to in a minute. So you can create them, drop them, and alter the schema for them, but you can't change individual entries in it. And then finally, as I mentioned, you can plug in custom scripts to do extra stuff that SQL can't do for you. So actually that might be one reason, even if your data is quite small, that might be one reason why you'd end up doing it on Hadoop. If you discover that you just can't write the types of queries you want in SQL, this might be a way of doing it.
So this is how NFS downloads it while on a local machine.
No. The only thing that ever comes back to the local machine is the, well maybe this is what you're asking, is the results table if you explicitly ask it to store it locally.
Yeah, but in the network file system, what we do basically, we mount a hierarchical structure on the local machine.
Oh no, it's not doing that. It's not doing that. No.
We have a store procedure in Hive as well. Store,
Yeah.
a store procedure. It's like store procedure. That we already created a procedure in function.
Oh, stored procedures.
Sorry.
Good question. I don't think so.
Well,
I'm not sure. No, I don't think triggers, because it's not that kind of, you know, you'd put a trigger if a record is updated or something, and you don't do that. It's just streaming in. So
are we able to like have two tables, two files, the streaming data is coming to the two tables,
yes.
and we have a runtime application who is getting this information. The output goes to the other table without writing the directory, like kind of related. As soon as these two data is coming.
Not within Hive, no. You program that in something else. Yeah. Okay, right. So partitions. So one of the fundamental things about MapReduce is that you've always got this idea of a key, right? Something you're doing a group by. That's at the heart of what map outputs, is a key and a value. And that's what the reducer gets, a key and a list of values and so on. And so given that we're probably going to want to organize our data around subsets of that data that share the same value, it makes sense if when we organize it physically, all of those values are kept together in the same place, right? So if you then wanted to say, give me everything where this has this particular value, they're all there in one place. And if you define from the start, before the data starts to come in, if you define something called a partition on Hive, then that does exactly that. It stores it stores the data associated with certain values of variables that you've chosen all together in one place. And actually it cuts down on the amount of data stored very slightly as well, because it stores it all in a file where everything in that file has the same value in one of the columns, or sometimes more of the columns. So, I don't know, let's say we partition on age, and we have one file for everybody whose age is 25 and another one for 26 and so on. You don't need to store a column with the number 26 in it for everything in that file, right? Because that's the file for the 26-year-olds. So it cuts down on the amount of data stored slightly. That's not really the point. The point is that it keeps them all together, so that if you want to do some process only on a certain subset, it's all there, all together in one file. So it's partitioned, well, either on discrete values or on bins. We'll come back to the bins. The idea of a partition is that it's just discrete values. We'll talk about buckets, they call it, when it's across a range in a minute. And so that allows us fast access to all the data with certain value, right? So if you say, give me all the 26-year-olds, it doesn't have to go across the entire network to find them all. It just finds them all in one place, which might speed things up, but you can also imagine it might slow things down, right? Because now you're asking one machine to do all the work for that query rather than spreading it across several machines. So sometimes whether or not that's the thing to do depends on how you're going to be using it. You can also partition on more than one field. Again, they have to be discrete values. So here in my example I've done on age and gender. And then I get a unique file for every combination. All right. So let's say, I don't know, in the data I stored there happen to be, I don't know, let's say 80 different ages. So we have 160 files, assuming every combination was touched upon, which, well, that's okay, that's not too many. You need to be careful that you don't get thousands and thousands of files, because as we know, HDFS can't cope with that so well. But generally speaking, the partitions are supposed to have a reasonably low cardinality. That is, they don't have too many different values, because we don't want the number of files to get really large. So each partition has its own directory in HDFS, so remember still it's actually building a file structure here, which makes it a bit different from a normal database, right? If you've got a normal database, you don't tend to be able to dive into the file structure behind it and have a look at anything. Whereas here you can. It's just imposing something on the HDFS file structure. And there's a link at the bottom there if you want to read a nice article about using partitions. Right, okay, so I'll talk about inserting data later on, but it has a nice facility where if you've got a block of data to insert and it all belongs to the same partition, then you can tell it that and it puts it all into that partition all in one go. You gain a bit of writing efficiency. And actually, from, well, a few versions ago now, it offers this dynamic partitioning which organises it all for you. So you just, once you've set up the partitioning, it works out where everything has to go. Okay, so that's partitions. Are there any questions about that? It's quite straightforward, really. And so we've also got this idea of buckets, which is basically the same idea as partitioning, except you can apply it if there's perhaps a numeric range, or if there are values that have too many, variables, columns that have too many different values to split it up. So we don't want hundreds and hundreds of different subdirectories, each with a small amount of data in it. It's very inefficient. So we can put it together into buckets. And generally, as we've learned in other things, which are similar to this is achieved with a hash function. So we define a hash function which takes the data that's actually in the column as an input and produces as an output, I don't know, a number from 1 to 10, for example, whatever you've defined. If you want 10 partitions, it maps all the possible inputs onto one of, let's say, 10 outputs. And then you've got 10 buckets. And that makes sure that data, all the data with the same value is all in the same place, but it's accompanied in that same place by data with other different values as well. So you still get some efficiency of knowing that if I want data in this range, it's all on this machine, but you've still got to scan through to find it. But still, it's a little bit more efficient. Yeah, and as I said, you fix the number of buckets that you want, and then Hive organises the data for you.
It's like making the beans.
Making the what? Bins. Well, yeah, it depends on the hash function. So you can have it range-based, in which case they are bins, or if you have a hash function, then it spreads them more evenly. Much like, remember the range-based hashing and the the range-based partitioning and the hash-based partitioning in Mongo? Exactly the same idea. Range-based keeps them all together in ranges, but risks overloading one, in this case, bucket with lots in it, depending on how you've set it up. Whereas a hash has a nice even distribution, but things that are next to each other in the data space could be separated in the hashed space. Yeah, so it just depends how you define it. Okay, so running Hive is pretty straightforward. You log into Hadoop in the normal way and you type Hive, and then you get the Hive command line. And from there, you can start typing some commands. So let's have a look at a few examples. So the first thing to do is create a database. And again, these are slides from when home used to be home. It's now user. So I should really go through and change all of those. So if I want to create a database, I type create database, give it a name, location, and then this is a directory in HDFS. So that tells it that this folder, see, remember it's all around folders, so again a slight difference from how you create a database. One of the ideas of traditional databases is that there's an abstraction away from the file store. You don't need to know anything about the file store to build a database. Whereas here they're more tightly connected, right? So we're actually saying this is where I want my database to live. And we've got these semicolons at the end of the lines. And then let's just see if it found it and did it. So I type describe database and the name. And then if I want to use it so that I don't have to keep telling it to refer to that one in each of the subsequent commands, I can type use and the name of the database. And from now on, that's the one it's going to be looking at. Okay? Yeah?
It's no database where we're creating a database.
If there's no data. Yes, at this stage, I am actually creating a database that's going to hold some data. I'll show you in a minute if there's already data there, what happens. So this is me preparing some space for some data.
This is the display structure of the database.
Yes, yes. Which at that point wouldn't have had anything in it. Yeah. But now I'm going to put something in it, so it would have then the same as the SQL describer. So I'm going to create a table, and you'll recognize half of this as being exactly like SQL, and the other half as having some new stuff. So I created a table, I've called it my table. I've defined a field called age, which is an integer, and I've added a comment about that, which obviously is just for admin. And then another one named string. So I've got two columns, each of them with, oh, and then I've got a comment about the table. And then the next two things are Hive specific commands. So I'm telling it to partition by a field called gender. And you'll notice that I haven't included that in here because it's not going to be one of the columns. When the data comes in, it's expecting to find a gender value, but that just tells it which subdirectory to put it in. It's not stored in the actual table like I described, so that's why that's like that. And we're clustering by age, and we do need to store the age because the hashing algorithm doesn't define exactly. There might be 30 or 40 different ages all in the one bucket, right? So we've still got to store the actual age. So you can kind of see the difference between those two things there. No, which is what I'm saying here. Partition introduces a new variable, as I said, and cluster uses one that's existing. Everyone see why that is?
How does the database knows about 10 buckets, which range of the edge? When you say buckets, clustered in 10 buckets, okay, sorry. I got my answer.
You got it right. If only all questions were that easy. Right. So, yeah, we defined, in my example there, we defined it as an int, and it has a bunch of data types that you'll recognize if you've ever used an SQL database. So there's probably not much need for me to read those out. It also, on top of that, has a number of complex types, ways of organizing the data into something that's not just an integer or a string. So you can have what's called a struct, a structure, which has, it's a bit like an object, right? So we have an object in Java, so we've got an integer which is A and an integer which is B, and if we call the whole thing C, then C.A refers to this one and C.B refers to this one, just like if we had a Java object that I called C, and I had accessed the member variables A and B in it. So it's, you know, kind of similar idea to that. And then maps, I suspect you're all used to hash maps by now. So we can define a map, say I've called it M, and now they're accessed by an index. So we're using the array, associative array indexing style, where we use the name of the variable, square brackets, and a string inside to tell it the value of the key that we're referring to look up the value that's stored. You've come across those before, or is it evident what's happening from that? See that? Okay. And then finally, numeric arrays. So a numeric array is indexed by integers 0, 1, 2, 3, 4 and so on. And a map is basically an array, but it's indexed by strings. So obviously they don't have an ordering like the array does, but you can see the relationship between those two things. So we can define those and store them straight into columns in Hive as well. Right, okay, so on top of the SQL functions that you would expect, Hive has a bunch of built-in functions, ones that are kind of nice to implement in MapReduce, the kinds of things that you would expect somebody who wants to store their data on Hadoop and on HDFS and run a Hadoop-like thing. And rather than list them all here, if you want to see them all, you just type show functions in the command line interface, that's what CLI is there, and it'll tell you what all the functions available are. And if you want to know more about any one of them, type describe function and then the name of it, and it'll tell you what it does and how to use it. So, right, okay, so we've set up our table, we're ready to put some data into it. We have put some data into it, and we want to read some data from it. So I guess this is the kind of simplest select here, and because the result of a query is always written to a table, we've got this extra bit at the start of our query that tells it where to go. So insert, now here's the answer to your question about whether we overwrite or not. If we overwrite there, then we do. If we don't put that, then it complains. And then this is the name of the table that we want it to go in. And if we've already said use database, whatever we've called it, inside Hive, then that will go into a folder underneath the directory that we chose when we first set up the database a few slides ago. So that's where that goes, and then here I'm just selecting from the table where, so column A, that means not cola, equals some value, right? So that's the kind of simple version. You'll recognize this, and it's just this extra bit at the top. Sorry, I'm using the mouse and that doesn't work up there, does it? You recognize the select from and so on, and just that top bit is telling it where to put it. And then you can go into HDFS, look at the contents of that file, and see what you've got. So that's pretty SQL-like. Inserting is slightly different, because although you can type an SQL-like insert, so we've got one here, inserting the table, whatever the table's called, values, and then because each interaction with the database takes some time, it starts up the VM, it runs the thing, and so on. And because the whole point of this is that we're streaming data in at speed, generally speaking, unless you're just playing around at the command line to, have your first go at Hive, you're not going to be entering data into it using that syntax up there. So instead of that, it's got this load data command, which is much faster and takes a bulk of data and puts it all in one go. So we've got load data, then we've got a path of where the data is going to come from, whether or not we want to overwrite the table, the name of the table in HDFS that we want it to go into, and then because the data that's coming in, if it's partitioned, we need to tell it where to go. We can optionally define what the partitions are. And then we've got this final thing which I skipped over, local, tells it whether this file path, local there, tells it whether the file path is in your local space or on HDFS. So if you type local, it grabs the file from local, and otherwise it grabs it from HDFS. Yeah.
So before you said that, for example, in the partition there were the gender.
Yeah.
Okay. So here you need to know which are the values for the gender.
You need to know where it is, which column. Well, I said, yeah, so this one is assuming that the entire contents of the data that we're going to load are all destined for the same partition. So in my example here, I've got, I've partitioned on 2 fields, and so, I don't know, remember we did age and gender? So that might say,
the name of the column.
yes, equals age equals, well, sorry, equals 32, age equals 32, gender equals male, for example. And that would put them all in the partition for that. And as I said, they've got this auto, from now, the later versions have got this auto partition where it'll extract it for you from columns and put it in the right place. So yeah, that particular example is where all the data in the file belongs in the one partition.
It's the name of the column, it's not the value.
No, it's the value. So we're saying they're 32 and they're male, for example.
So we
So-
need to know.
Yes, you need to know. Yes, yes.
So this load command basically loads data into the local memory, or it is?
No, right, well, so it stores it in HDFS, that's what it's doing. If you give it a local file name, then there's actual data transfer takes place. It grabs it, so it's doing a copy from local basically, takes it from local, puts it into HDFS, imposes whatever schema around it you've defined. If it's already in HDFS, then you're just imposing a schema on it so that you can then access that data in the way that we've been talking about here.
The file you're sending is that have a different columns.
Is what, sorry?
The file path. Is the file name
File
itself?
path, yes, so file path is its location either in HDFS or in your local store,
Okay.
depending on whether you write the word local or not.
But
So-
when you're saying the sending, loading data means loading the file.
A
yeah?
file,
Yeah.
yes,
Is that
yes.
have many records?
Yes, many records, that's
Okay.
the idea.
And if the records have many different ages, what is going to be the value 1? Value 1?
Yeah, oh, well, no, you wouldn't use that syntax for that. That's syntax, see the square brackets around it, so that's optional. And you would use that if the whole file is in a particular single partition and you're defining what the partition is. Otherwise, you'd use the auto partitioning. Yeah, and if the file path, even in HDFS, if the file path here is not where the data for your database is stored, it'll copy it across from HDFS. So you need to be a little bit careful. You might end up with 2 copies in HDFS that you don't necessarily want. Right, okay. So as I've already said, the files are just stored, sorry, the data is just stored in files in HDFS. And you can tell it, well, you've got a couple of options. You can tell it whether to store it as a straightforward text file, or do you remember a few lectures ago we talked about sequence files, which are particular format of data designed to be stored in HDFS with extra stuff in the header about things like compression and an ability, and things like markers to say where to split the data and so on. So they're kind of HDFS aware files. So you can store just raw text, or you can store sequence files, which gives you a kind of broader set of application if you want to use those. And then finally, remember I said in the last slide, if you've got the data in HDFS but in a different location, it actually copies it from that HDFS location to where your database is. And you might know if it's huge, you don't want to be doing that, right? You don't want to be duplicating it. So finally, we've got this thing here where if the data is already in HDFS at the location at the very bottom there, that command says, don't copy the data, leave it where it is, but just turn it into a Hive. Well, it doesn't change the structure of the data. Impose on top of it a schema so that I can use it in Hive. All right. So we're not duplicating it. It's not in a file here and in a database there. It is just the file, but we're telling Hive how to read that file and treat it in a tabular form. Does that make sense?
How come this user ID is each data type? Because we use normally in data type where computation is involved. Like we want to calculate a driver value.
Yeah.
User ID is,
Should be a string.
yeah.
Okay, so right, so we've got the data in. We've done some very simple selects. You can do other things using that SQL-like syntax. If you're not sure how to do it in Hive, do it the way you would in SQL and see if it likes it. There are some things that it doesn't, but you know, you're kind of 80% of the way there if you know SQL. Or, you know, at least that tells you what to look up in the Hive manual if you know what the SQL equivalent is. So we can do joins, we can do aggregations using group by. So you can pretty quickly guess, you know, if you know SQL, you can pretty quickly work out how to interact with Hive. And I've said already you can store the data, the results of your query back into HDFS, or you can do it straight into your local space. So for you guys, that would be your H drive, by insert overwrite local directory and then where I want it to go. So for you, it would be /user/username, wherever you want it to go. And then you do your select. So a very simple select here. And what that will do is it runs the query on HDFS and then sends it back out of HDFS into your local space, into a file that you can then open and look at in your favourite text editor or spreadsheet or whatever it is you want to look at it in.
Does it support equal and only, or you can use inner outer joins as well in this file?
Not sure about the inner or the outer joins. Yeah, can't remember off the top of my head, sorry. Look at that. Right, okay, how are we doing? Oh, that's good. And then finally, on top of all that SQL goodness, if you've been using Hive and you long for those days where you had to write a mapper and a reducer, which seems unlikely, then you can also write your own custom MapReduce code. So you've got the basic set of things that SQL offers, but they are kind of limited, right? There's a certain set of aggregations you can do, but there are lots that you can't. For example, you can't ask for the median of a column, or not easily. You can't ask for select the top 25 percentile or some such, right? These things start to get a bit more tricky. But if you can write a map and a reduce code, then you can make your query do whatever you want. You're back to just writing Java. But actually wrapping it up in Hive still makes those things a little bit easier. So you can write a custom mapper, a custom reducer. Actually, you can, as long as the nodes have a compiler or an interpreter for your language of choice, you don't even have to write that bit in Java. You can write it in something else. It's just telling it what to do in the mapper. And it has this extra bit of flexibility in that instead of having a context to read from and a context to write to, it has this more general thing where your program just has to read from standard in. Actually, I don't think we've done that yet, but it's just a standard stream. Okay, so you open standard in as if you were opening a file, and you read from standard in, and Hive organizes it for you so that the data that's coming out of the file that would go into your mapper as key value pairs is just read from standard in. So your program just keeps reading it from standard in, and then instead of emitting, it just writes it to standard out, and again Hive collects it from there and makes sure it goes off to the right place in the MapReduce process. And that's what really frees you up to use other programming languages, because as long as your programming language can read from standard in and write standard out, and all of them can, and of course the nodes know how to run it, then you're freed up. So basically a mixture of SQL and your favorite programming language, you can run whatever queries you want across all of the data in your files. So it's quite a nice combination of ways of doing things. But it's now based on columns. It's got this more database-like idea where if you said select column A and column B, then standard in provides column A and column B for your mapper. All right. And it doesn't use all of that Apache Hadoop map and reduce class stuff that we've already talked about. It just has to, as I said, read it from standard in, do something with it, and send it back out to standard out. So in some ways, there's a lot of simplification for you in doing it that way. So if you want to read a bit more about how to do that, custom mapping and reducing, these are a bit old now, but they're still quite good articles. There's a couple of links there. You can follow them off the web page. Right, okay, so there's a bit of a quick race through Hive, but I think you now know what it is and what it's for. So it's not a database, but it kind of looks like one from certain angles. But still we're writing to it once and we're reading large chunks of it many times. All right, we're not interacting with it transactionally. But we do get this nice SQL-like language. Behind the scenes, we write select A from B where C equals something, and it runs a MapReduce job behind the scenes. So exactly that stuff that you have been doing in the lab already, that's what Hive's doing, but it's giving you a nicer interface to that. And I talked about partitions to improve the speed of certain queries, and I said it's not good for this kind of read-write interaction. Yep.
Are we going to use these in the lab?
There isn't a lab on it, no, but you can... actually, it struck me as I read that out that you could do that. I hadn't thought to check whether Sam reinstalled it. I'd give it a few days just in... Well, have a go. Right, have a go. If you type Hive and nothing happens, then try again in 3 or 4 days. I'll have a word with Sam afterwards. It did occur to me as I said that yeah, I don't know. I wanted to pick one of the other Apache... I mean, there's so many now. You could have an entire course on each of the extra things that they've added onto it. And I don't know, I wanted to pick one to tell you about, and this was the one, but I guess it's slightly peripheral. And in the next 3 lectures, hopefully that's what I'll fit it into, we'll have a look at Spark, which we'll do in a bit more detail, in which there is a lab about. And yeah, it is a bit more what we're going to be trying to do. So, okay, good. And oh yes, remember there is one at 5 today. Yeah, at 5. Yeah.